My dear students, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I would like to welcome you all to our International Physics webinar. So, good afternoon to all. So, I hope you are well and safe from Corona pandemic. So, as you know that we are staying in a Corona pandemic situation, so it's very difficult for us to continue our normal academic program inside the campus. So, we have to start our online program. I think we have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including online international physics webinar, and we have successfully completed our 190th international physics webinar. Today it's our 191st international physics webinar, and uh, we have with us here today Dr. Professor Naba K. Mondal, sir, former senior professor, Tata Institute of Fundamental Research, Mumbai, India, and currently he is working as a INSA senior scientist, Saha Institute of Nuclear Physics, Kolkata, India, and he has already connected with us. So, sir, good afternoon, and thanks for joining with us, and thanks for giving us this opportunity to arrange this important webinar with you. So before going to you, I'd like to introduce you with our student and viewers. So for those who are new, I'd like to inform you all that we have divided our webinar into three parts. First of all, I would like to introduce our speaker with all of you, and then our speaker will deliver his piece, and at the end we have a discussion time. In that time, anybody can join with us. And you can also ask question by commenting. I think you have already come to know the title of this today's international physics webinar, and the title is the particle physics and its role in early universe. Very exciting and interesting topic. I think you will enjoy it. And our speaker is Professor Naba Kumar Mondal, sir, former senior professor, Tata Institute of Fundamental Research, Mumbai, India, and currently he is working as a INSA senior scientist, Institute of Nuclear Physics, Kolkata, India. So, Dr. Uh, uh, our Naba K. Mondal sir completed his bachelor degree from the University of Burdwan in 1972 and master's degree 1974 from the same university, and he completed his PhD from Tata Institute of Fundamental Research in 1983. And we can see Professor Naba K. Mondal joined Tata Institute of Fundamental Research in 1979 and was associated with the pioneering polar gold field KFG, KGF proton decay experiment from its inception. During 1985 to 1986, he was a visiting scientist at Aguni National Laboratory, USA, and was involved in the design of the second generation nuclear decay detector called Southern 2. During 1986-1987, while on a long visit to Wisconsin University, USA, Professor Mondal worked for the Collider Detector Facility, CDF, at Fermilab, USA, and he participated actively in the design and fabrication on the forward tracking chamber for the experiment as well as in the physics analysis. In 1991, Professor K. Mondal and his group who joined the International Collaboration Experiment called DQ at a Tevatron Collider at Fermilab. He was involved in the important discovery of top quark, which was the last missing quark in the standard model of the particle physics. He also used the DQ data to put strong constraint on masses of SUSY particle and extra dimension parameters. He also looked for substructures inside quarks and leptons. American Physical Society presented him the S3rd Hoffman-Beller Endowment Lecture Awards in 2001, and in 1995, Professor Mondal and his group joined the CMS experiment at Large Hadron Collider LHC project at CERN, Geneva. He was the technical coordinator for the CMS Outer Hadron Collider project and was instrumental in the design of this sub-detector and led the Indian team during its research and development phase. Professor Mondal is now involved in the development of a world-class underground laboratory in India for carrying out research in the emerging field of neutrino physics, a collaboration of more than 100 physicists and engineers from various research institutes and universities in India has been formed under the leadership for the development of India-based neutrino observatory. The aim is to make precision measurements of the parameters related to neutrino oscillation. So thanks all of your patience. Now it's time to go to our speaker. Sir, I'd like to welcome you again, and thanks again for giving us this opportunity to attend such an important webinar on particle physics and its role in early universe. So thanks again, sir. It's your time, sir. You can start your session.
Thank you. Thank you, Pretam, for your
It's my
introduction
pleasure,
and
sir.
for even inviting me to talk in this webinar series that you have started at your university. So,
Thanks, sir.
I am basically a particle physicist, and as a particle physicist, I looked into subatomic, matter and the structure inside atoms and what the everything is made out of. It's the smallest structure that we can think of the universe. On the other hand, the there are my colleagues like cosmologists and astrophysicists. They look at the whole universe as such, and looking at its evolution, its structure, and its origin, and so on. However, at certain part in the evolution of the universe, these two kinds of physicists, that is the particle physicist and astrophysicist and cosmologist, have to come together to understand the very early part of the evolution of our universe. And I am going to talk about today what the information that we use from particle physicists to understand the evolution of the very early part of the universe. So this is my topic. Now let me start with first with the universe as such. So it's if you look at this beautiful night sky, you see all those stars in the sky and galaxies and so on, and you start wondering how all these stars have evolved and where they are coming from and where they are going to end. And to understand this basic, whole universe, we have used one instrument, and that instrument is our telescope. Okay, the telescope, originally started by Galileo, has changed over the time, has evolved, but its basic principle is the same. It just collects the light from distant objects and we start looking into those objects. So now this the telescope that was used by Galileo may be very small, but over the years, hundreds of years, we have made bigger and bigger telescope and put them on the mountain top and so on. And sometimes the structure of this telescope looks different because we look at the different spectrum of the whole electromagnetic spectrum that is coming out from the stars, right? For example, in the bottom here, I'm showing you the radio telescope that we have in India near Pune, and they are looking into the radio wave that are coming from those distant stars and galaxies. On the other hand, the telescope that I'm showing on the top, they are mostly looking into the visible light. So you can look into all those lights, but remember, they are all electromagnetic spectrum, right? Starting from gamma rays, on the other hand, to the radio wave, in the other extreme, we all looking into these electromagnetic emission coming out from the objects. And sometimes even those telescopes we are sending into the space. For example, here is the Hubble Space Telescope, which was located in the space, not even in the ground, just basically to avoid the absorption of light by our atmosphere. So now, using all these telescopes that we have, what we have learned so far. Now let me take you through a journey that, let's say you are sitting on a spaceship and you have a telescope with you, and we are moving away from the Earth, okay, with certain velocity, and how your field of view is going to change, what you are going to see. Imagine that on the journey. So now if you are away from our Earth and looking from a spaceship toward the Earth, you will see through the telescope a picture of our Earth. And what is the size of our Earth? The size of our Earth is something like 12,700 kilometers in diameter, right? So this is the Earth you will see, and this is the size of your field of view of your telescope at this moment. Now you are going away from the Earth, so your field of view is going to increase. So you will suddenly, after some time, you will start seeing the Earth and its nearest object. Its nearest object is the moon. And what is the distance between them? Now we have now come to something like 400,000 kilometers. is the distance of the moon from our Earth. So this is our field of view, something like 400,000 kilometers that we are seeing from a telescope sitting in a spaceship going away from the Earth. If you go far away from our solar system, then you start seeing the whole solar system. Okay, now what is the size of your field of view? It's actually something like 6 billion kilometers, much larger than what we had seen earlier. And we started seeing all the sun and all the planets and so on. And you start moving away further and further in your spaceship. Now, next thing you will see the whole galaxy, our galaxy that is called Milky Way galaxy. And our solar system or the sun is only a small star in this whole galaxy of billions of stars together. And this is the whole structure of our Milky Way galaxy. And what is the size of that galaxy now? It's 100,000 light years. Now I am not talking about anymore about kilometers, because it will be a big number. So what I am talking about now, light years. And a light years is that the distance a light travels in 1 year. And this is actually given by something like 10 into 10 to the power 12 kilometers. So 10 trillion kilometers is 1 light years. And in that, the sun actually is not even in the center of our galaxies. It's far away, something like 26,000 light years away from the center of the galaxy is the sun located. So sun is just a small, insignificant star in our own galaxy. Okay. Now, you still go, your spaceship is going away again further from the Milky Way galaxy. Now you will start seeing the other galaxies. For example, you will see the Milky Way galaxy and its nearest Andromeda galaxy, which is 2.5 million light years away from our Milky Way galaxy. So you'll start seeing these objects together. But then if you go and if you increase the field of view to something like 500 million light years wide, then you'll start see not one or two galaxies, the cluster of galaxies, which you call a supercluster. And the galaxies are together to form a supercluster. And ultimately, this is not a picture, but a computer-generated picture of how the whole universe look like. It's just a connection of those galaxies through a cosmic wave of voids and superclusters of galaxies. This is how the universe will look like when you look into the deep inside it. Now, another point you should remember at this moment is that when you are looking into this galaxy far away, you are not looking at the galaxies what it looks like today, because even light takes time to reach us from those galaxies. For example, even from the sun, when we look at the sun, we don't see the sun at this moment. We see the sun when it was 8 minutes earlier, okay? And so on. So now, what is the first, if you go back like in time, what is the first picture of the early universe you will see using the electromagnetic spectrum? Okay, this was what I'm showing is the first picture of our galaxy, which is no more like of our universe, which is no more anymore like those combination of galaxies, so on. It is just a very uniform, homogenized, space where every part of the universe looks similar. And this is actually the first picture of the early universe, which was actually after something like 400,000, actually 380,000 years after the creation of the universe. And this we'll see through the radio waves using this Planck telescope. There are quite a few were sent, but this is the Planck telescope. So this we'll see the universe was uniform in temperature and uniform in matter and so on. Okay, almost uniform. There was no galaxies, no star, nothing. And this is the first picture of the universe we get. We don't get any information by looking at the light coming from the universe or using our telescope. So how the universe was before this 380,000 years years after the Big Bang. So from the beginning of the universe till 380,000 years, how was the universe was? The universe was, of course, very dense and very, very hot and very dense. It was so dense, and even the light was never used to come out of that period of the universe. So if and our all knowledge so far about the universe is by looking at light coming out from the different objects. So if even light is not coming out from the universe, then how do we look at those periods? And that's the question that we have to answer. And for example, why light was not coming out of the universe before this time? This is because when the universe was younger than 380,000 years, then what was the universe was look like? It was actually was an ionized gas. Okay, that means it has the hydrogen, nucleus, that is proton, and the electron. But the electrons are not going around the proton. So that means atom has not yet been formed. So it was an ionized gas. And because of that, the photons at that time used to get scattered by those charged particles. And they used to get scattered from one another and so on. So they have nothing, they could not come out of that universe. And that since light was not coming out, we have no way to look at that period of the universe. So what happens at 380,000 years at that time? Because the universe was cooling down, right? Over from the beginning, it was also cooling down. And at that time, after 380,000 years of this creation, the universe was cold enough so that the proton and the electron combined the hydrogen atom. Okay? And once the hydrogen atom, neutral atom, was formed, then there was no way the light was getting scattered. So then suddenly light was started coming out. And this is the first picture. Those light was the information we get about the universe. So using this light, we can get information what the universe was look like at 380,000 years. Before that, as I told you, no light was coming out, so we had no way of knowing how the universe was at that time. So then, how do we, know what the universe was earlier to that? And so before that, let me answer to some of the questions that we ask in astrophysics. So what we want to know, the basic question is, what is the basic structure of the universe? That what it is made out of, its origin and its time evolution, how it has formed and how it has evolved over time. So this is the question we ask. What do we know till now? We know that I have shown the picture of these galaxies, that all these galaxies of our universe are moving apart from one another. That means the universe is expanding. Also, we also know that it is cooling down, that the universe, we can infer then from there that it was much denser in the past, it was much hotter in the past. It was so dense that even light was not coming out of that time. And it was, of course, very hot. And it was expanding. And its expansion is showing into the picture here. You think of a balloon and you are just blowing that balloon and its sizes increases. And if you have dots on that balloon, those are the galaxies. And then let's say as it expands, the galaxies are going away from each other. So all these galaxies are moving apart from each other. That's what we see now. So now I will change the gear and talk a little bit about another instrument, not anymore a telescope, but of a microscope. But not a microscope that the biologists use, but a microscope that particle physicists use. And particle physicist microscope is a little different than the picture I have shown here. Here is the picture, first picture of a particle physicist microscope. This is actually is the Rutherford experiment. When you want to know the structure of matter is the smallest scale, what you do, you basically bombard that particle by another energetic particle and break it apart, okay, and see what is inside. So if you want to see inside the atom, you have to hit the atom hard with some particle, and the atom will break down, and you can look into that inside that picture. And using, for example, this is the microscope that was used by Lord Rutherford and more than 100 years back. And this is what he has discovered, that the atom is not like a plum pudding model. It's not a homogeneous mixture of positive and negative charge inside that. And it is actually what we have is all the positive charge are concentrated at the center in the nucleus, and where all the mass of the atom lies, and the electrons are going around it in different orbits. And that picture was coming out from this experiment that Rutherford did in 1911. But from that time, many years, centuries have passed, and we have learned much more about particle physics, but our instrument that we use remain the same. We still continue to use the energetic particles, and one side, let's say energetic proton, and hits into another target, another matter or another proton, and then from that collision we create new particles, or we try to understand what is the structure of the matter or at the smallest scale. For example, this is the particle accelerator we are talking about, where you actually rotate in counter rotation of protons and antiprotons, or protons and protons. They collide after some time, and from that collision we create new particles and we understand the structure of matter. Here is a picture of one of those accelerators where protons and antiprotons used to collide, and that you have talked about in the introduction. This is the Tevatron collider at Fermilab, where top quark was discovered in 1994. And here is the picture of the Large Hadron Collider at CERN, Geneva, where experiment was conducted called CMS and Atlas, which has seen the Higgs boson. Okay, and in this collision, what will happen when the particle collide? This is the picture of the footprints of the new particle that was created in that collision. New particles will be created, and we basically understand their properties and so on. So now let us look into that what we have learned so far from this particle microscope. So for example, now what we have done so far, sorry, we just increase the resolution of our particle microscope. Now if our particle microscope has a resolution of 10 to the power minus 10 meter, okay, then what you will see the atom in this picture, that it is made out of a nucleus and the electrons are going around there. If we start increasing the resolving power of our particle microscope and focus into the nucleus, that tiny nucleus, so that nucleus is another something like 4 orders of magnitude smaller than the atomic size. And in that nucleus, if we can focus into that, then you will see that it's made out of compact object, and that is the protons and neutrons very tightly bound together. Okay. Now if we increase the resolution of our microscope further and start looking inside one of those protons or neutrons, then what we will see is that each of these protons and neutrons is made out inside that 3 particles. They are called quarks. Okay, these are the quarks. In fact, if you look carefully, they are not just 3 quarks. They are actually a sea of virtual particles blowing around that quarks also. The 3 quarks. So these are the 3 quarks, and then there are virtual quarks and gluons. Gluons are the particles which glue these quarks together, okay, inside the protons or inside the neutron. So each of these quarks, and then if we start looking further, if we increase the resolving power of our microscope, then we'll look into the quark itself, what we have learned. So for example, what is inside the quark? And till now, we have gone up to a scale of 10 to the power minus 18 meters. We have not found any structure inside the quark. So we believe that we have reached the ultimate building blocks of matter, which that every matter is made out of. So now, using that understanding, what we have learned so far, these are the elementary building blocks of matter. So matter is made out of some 12 fundamental particles divided into two families. They are called quarks. One family is called quarks and other family is called leptons. Okay, there are actually 6 quarks and six leptons. And these 6 quarks, they also divided into 3 families. The first one is up and down that I have shown in red, U and D. Then the next family is charm and strange, and the next family is top and bottom. In fact, once you go from the one family to the next, only their masses increases, but they look exactly similar. Similarly, in the leptons, we have the electron. We are all familiar with electron. And associated with that, a neutrino called electron neutrino. And then there are next family is called a muon. Muon is just like an electron. Okay? Muon is just like electron, but heavier than the electron. And muon also has its own neutrino associated with it called muon neutrino. And then there is a third generation, which is the tau particles and its own neutrino called tau neutrino. Okay, so this is the fermions. These are the particles, but we also have, Dirac has told us long back that every particle has its antiparticles. Okay, so similarly, all these quarks and leptons, they have their antiparticles. For example, up quark has an anti quark, anti up quark, down quark has an anti down quark, and so on. So all these particles have their antiparticles. Now, these are the fundamental building blocks of matter. But as I told you, which in the matter, they are not, we don't find quarks. We found protons, we found neutrons, we found just iron, oxygen, and so on. So how these elements are formed? They are formed by combining these elementary particles. For example, a proton, as I told you, is made out of 3 quarks. Actually, it is made out of 2 up quarks and 1 down quark. They are tightly bound. But which makes them bound together? What is that? That is actually another set of particles, and they are called bosons in the name of Satyam Bose. These bosons actually are the exchange force, because the particles, these quarks, they are exchanging a force between themselves, and because of this force, they come together. For example, in an atom, you know that there is a nucleus and the electron is going around it. Why the electron is going around it? They are tightly bound. Why? Because there is the electromagnetic force acting between the nucleus and the electron. Similarly, inside the proton, 3 quarks are bound together because there is another force called strong force that is acting among themselves. So there are actually, we know in nature, there are 4 forces: strong, weak, electromagnetic, and gravity. And gravity is the weakest. We know gravity. Gravity is responsible for the Earth going around the sun and the moon going around the Earth and so on. So this is gravity, and its ranges extends up to infinity. But there are some force like strong force. It's much stronger than gravity, but its ranges extend very small. It's only act when the particles or the quarks come very close to each other. Okay. Similarly, there is electromagnetic force, which also has an extension up to infinity. That is, its range is up to infinity, but it is much more stronger than gravity. And there is the 4th force is called weak force, which is responsible for certain decays, for certain material like uranium, thorium, and so on. The decays. That's basically for the weak forces. And how these forces work together? And there is, of course, Higgs boson. How these work forces together? When 2 particles come together, say 2 quarks come together, or an electron or a positron come together, or 2 electrons come together, they exchange these bosons. Okay, these bosons are the exchange particles that I'm showing in the green here. And when these particles exchange the bosons, and they will stick together because of these exchange particles. Okay, so this is how all the matters are formed. For example, when the electromagnetic force acts between the nucleus and the electron, we form the atom. When the strong force acts between the quark, we form the protons and neutrons. and of course when the gravitational force is acting upon matter, then this all the structure that we see around in the large scale, that is the planets going around the sun, or the sun moving into the galaxies, or galaxies come together into a supercluster, and so on. This is happening. These are all because of the forces, different kind of forces acting among the particles. Okay. Now, whatever I am talking about these particles so far, that is the quarks and electrons, they are basically what you call the baryonic matter. They only form the 4.6% of the whole universe energy budget. There are other matters in the universe called dark matter, which actually form the 23% of the total mass energy of the universe. And there is most of it, what you call now, is dark energy, which is something like 72% of the remaining energy budget of the universe. So we have not much learned so far. We know that dark matter exists, we know that dark energy exists, but we don't know details about this because we have not been able to identify what does the dark matter look like. But we know from our observational data that dark matter also should exist. Anyway, so now that is about the matter. Now let me give you a little more about these four forces that I am talking about. As I told you, the weakest of these forces is gravitational force. If you take the strength of the gravitational force as 1, then the electromagnetic force, okay, its strength is 10 to the power 36 times, much higher than the gravitational force. The strong force, even higher, something like 10 to the power 38 times stronger than the gravitational force. And weak force is not that strong, but even that is 10 to the power 25 times stronger than the gravitational force. Okay? And these forces in nature that we see today is and other things. Now, while I am talking about these four forces, and they are completely looks different, their strengths are different, but there are also certain similarities. And these similarities actually makes us to believe that these four forces are manifestation or low energy manifestation of the same forces. That means probably at very high temperature at the beginning of our universe, there was only a single force, and that force later branched off into different forces like strong, weak, electromagnetic, and gravity. So this picture actually is shown in this cartoon diagram that I have shown. Let's go from bottom to up, and in the bottom you see at the current time. Okay, at the current time, the temperature of our universe is very low. Its average temperature of our universe is only 3 degree Kelvin. Okay, today the average temperature of our universe is 3 degree Kelvin. At this temperature, we have these four forces: strong, weak, electromagnetic, and gravity. Now, if you go up in the early universe, when the universe was hotter than what it was now, then at some stage, when the temperature of the universe became 10 to the power 15 degree Kelvin, or in other words, if you convert into energy, then it is 100 GeV, then this weak and electromagnetic force will combine together into a single force, and it is called electromagnetic force. So from that time onward, you will have three forces: electroweak, and the strong, and gravity. And then you go further back into the history of our universe, when the universe was much hotter, say something like 10 to the power 14 GeV. From 100 GeV, 10 to the power 2 GeV, now you have gone to something 12 orders of higher energy, or from 10 to the power 15 degree Kelvin to something like 10 to the power 27 degree Kelvin. At that time, we believed that strong, and now it is combined electric force and strong force. These two forces combine together to form a single force called grand unified force. And at that time, we had two forces: grand unified force, and which is the combination of strong, weak, and electromagnetic, and the gravity. If you go further in temperature or in energy and reach something like 10 to the power 32 Kelvin, it's a very high temperature. This temperature you cannot create in our universe now, but this temperature existed in the early part of our universe. And when the temperature was 10 to the power 32 degree Kelvin, or the energy at that time was 10 to the power something like 19 GeV, then all the four forces, strong, weak, electromagnetic, as well as gravity, combine into a single force called super force. And actually, so our universe at the beginning, we have this only one force, and from that one force split into two forces, and from there at present four forces. And this splitting happened when there is a phase transition. Okay, I'll come to the phase transition little just in the next slide, but this you understand, over the evolution of our universe, we started at the early stage into as a single force. From there we got two forces, and from there three forces, and then finally four forces. Okay, at low temperature. So now this, if I talking about this phase transition, I will be talking about binding energy. Now, what is binding energy? Binding energy is the energy that we need to break apart different phases of matter. Okay? It can be expressed as an equivalent binding temperature also. So now, for example, to give you an example, here is a piece of ice, and if you put that ice on a frying pan, what will happen? The ice will melt into water. So the phase of the matter, that is ice, get converted into that of water. Okay, this is the phase transition. We know that. In similarly, so if you goes on increasing the temperature of our universe, okay, what will happen? So if you reach a temperature of 10 to the power 3 degree Kelvin, then the atoms will melt. What do you mean by atoms will melt? That means the atoms will break apart into a positively charged nucleus and negatively charged electron, free from each other. The electrons are not anymore going around the nucleus. They are not bound together. So they're unbinded, right? So this is called melting. I am calling it melting. So atoms will melt at 10 to the power 3 degree Kelvin. Now, what is there inside atom? Now it has melted into electron and nucleus. Nucleus is, what is nucleus? It is actually combinations of protons or neutrons. So if you increase the temperature to 10 to the power 10 degree Kelvin, then the nucleus will melt. What do you mean by nucleus will melt? That means the protons and neutrons will fall apart from each other. They are not anymore tightly bound to each other. They'll just fall apart. So they'll get separated. So that is melting. Now if we increase the temperature of our universe further, or then even the protons and neutrons will melt. What do you mean by protons and neutrons will melt? I told you at the earlier that the proton is made out of 3 quarks. Neutron is made out of 3 quarks. So the protons will melt into 3 quarks. Okay? Neutrons will melt into 3 quarks. And then finally, the quarks will become completely free if you increase the temperature to 10 to the power minus 13 degree Kelvin. Then the quarks and antiquarks will be produced, and so on. So this is how what will happen if we increase the temperature of our universe. But we can't increase the temperature of our universe because we go in one direction. We are getting, the universe is getting cooler and cooler. But this was there once upon a time at the early phase of universe. This temperature existed. So once this temperature existed, how was the matter there at that time? So this is the next part of this story, or the final part of my story. So now let's talk about, so instead of going from current phase to the early phase, I will do the opposite. I will start from the early phase of our creation of our universe and slowly coming down toward the later phase. And I am talking about that part of the universe which you cannot be seen through your telescope, simply because I told you earlier that during the early part of the universe was so dense, so hot, that light was not coming out. Light was trapped inside the universe. And if the light is not coming out, I won't be able to detect that light, and then I won't be able to see the universe. So now let me start from the beginning. That is the creation of the Big Bang. But really speaking, we even can't talk about the beginning, real beginning, because the mathematics that we know need to understand the beginning is not yet there. So at the moment, the earliest part that I will be talking about is something like 10 to the power minus 43 second after the creation of the universe. Or in other words, when the universe was, so you go to the very left part of my picture that I'm showing it now, when the temperature was 10 to the power 32 degree Kelvin. Very, very hot, 10 to the power 32 degree Kelvin. Today, the temperature is only 3 degree Kelvin. Okay, so imagine how hot and how dense was the universe at that time. What is so special about 10 to the power minus 43 second that I'm talking about? In fact, it is the time, till that time, all those four forces that I'm talking about are a single force, super force, strong, weak, electromagnetic, gravity. They are not there in separate form. They are only one force. All are combined into a single force. So, the space-time that we know today has not yet developed, because space-time will develop when gravity will decouple. So space-time has not even developed what we think today. So how was the universe was that time? We don't know, really speaking. If you ask us today, what was the universe like before this time, that before 10 to the power minus 43 second, we won't be able to answer that, because we don't know yet how to handle gravity in the quantum form, and that is our problem yet. And many bright brains in the world today is working to find a solution and how to give us insight into how the universe was then. But as of today, we don't have a clear picture. So let me talk about 10 to the power minus 43 second onward. So at 10 to the power minus 43 second onward, what happens at that point, the Planck epoch, when all the forces were together, that ends. And the gravity decoupled from the rest at that moment. So this is a phase transition happening at that time, the first phase transition, that gravity decoupled from the rest. The rest was still a single force, that is called the grand unified force of strong, weak, and electromagnetic. So at 10 to the power minus 43 second, we got gravity and another force called grand unified force. Okay, so this was the time when it happening, and at that time, how was the matter? And then space, because gravity decoupled, gravity came into existence. So space-time started forming as we know today. However, what was happening in that, the quarks and anti-quarks are there, and they are annihilated, but they are not in the current form, not like even current quark. They are getting created and destroyed. Okay, the two quark, a quark and anti-quark is coming, annihilating each other, creating photon. Photons again coming together, forming a quark anti-quark pair, and so on. So this was happening, and then this suddenly around 10 to the power minus 35 second, this epoch ended. That means the Garth epoch ended. And what is happening? Garth epoch ended means the strong force decoupled from the other two forces. So before that, already at 10 to the power minus 43 second, the gravity decoupled from the rest of the forces, and after some time at 10 to the power minus 35 second, the strong forces decoupled from weak and electromagnetic forces. So at that time we had three forces: strong, electroweak force, and gravity. And this decoupling of the strong force from the electroweak force actually made something remarkable, something spectacular. What happens at that time? Suddenly, the universe started expanding very fast, in fact, exponentially. And exponentially, it expanded something like 10 to the power 26 times, okay, in size, within a very short span of time. Very short span of time, universe expanded. That's what you are seeing this picture here called inflation. And it means the universe expanded very fast. Okay, and this expansion, and then it after that expansion is over, what you call inflation, the universe actually slowly started evolving. I mean, that rapid expansion ended and the universe started evolving. Okay, so now the next, and then this reason for this inflation, and why do we need this inflation, is because there are certain properties, certain characteristics of our universe we have seen that needed this rapid expansion. Okay, but I'm not going into that details because let's not talk about that. Now what happened, the universe started cooling down from that time onward, and then universe when the universe was, next phase transition happened when the universe was 10 to the power minus 12 second. Okay, 10 to the power minus 12 second, billionth a trillionth of a second, and the temperature was something like 10 to the power 15 degree Kelvin. In that time, the next phase transition occurs when now the so we still have strong force and electroweak force. That means electromagnetic and weak force is still combined. And at that time, the electroweak force decoupled. That means it decoupled into weak force and electromagnetic force. So at 10 to the power 15 degree Kelvin onward, we have four forces of nature as we have seen today. Okay, so this is called the electroweak decoupling. And after that, when the decoupling happened and universe became cooler than 10 to the power 15 degree Kelvin, then started the quark epoch. Now that is the period when the quark gluon plasma was existed. That means quark was still free, but the quarks are interacting with each other through the exchange of gluons. Okay, so this is called the quark gluon plasma epoch or the quark epoch. And this lasted for something like some more time, up to 10 to the power minus 6 second. Okay, at 10 to the power minus 6 second, the quark freeze out started when the temperature was 10 to the power 13 degree Kelvin. That means now the universe was cold enough so that the quarks can combine to form hadron. That means inside the quarks getting combined and they are forming proton and neutron. Okay, so two up quarks and one down quark is forming into a proton, two down quark and one up quark forming into neutron. So this is called hadron epoch. Okay, now quarks are freezing out into hadrons, protons and neutrons are formed. Still, the neutrons are called free, and you know the neutrons are not stable particles; they also decay. But this time was so small that neutron didn't have any time to decay, and that happened little later when the universe was 1 second old. When the universe was 1 second old and the temperature was something like 10 to the power 10 degree Kelvin, then what happened? At that time, the leptons, what we call the lepton era, that is the temperature was so small or the density was such that the neutrinos, and there are actually, apart from quark, there are also neutrinos, there are electrons, there are positons in the universe. The neutrinos came out actually from the universe because they decoupled first. At 1 second, neutrinos decoupled, and these neutrinos, like these 3-degree black body radiation, the decoupled neutrinos, they spread out everywhere, and we see them now. We actually don't see them. We know that these neutrinos exist, but their energies are so small that we have no instrument to detect them yet. But we know that these neutrinos exist. And this happens at this time of when the universe was something like 1 second old. Okay? So now next thing is happening is that, so now the protons and neutrons is started decaying, because now neutrons, there is actually, even earlier the neutrons couldn't have decay because there was enough electrons and neutrinos in the soup. They will immediately put the neutron back. But once the neutrinos disappeared and the universe became little cooler, then the neutrons started decaying, and they decayed, and their number will become something like 1/5. That means every 5 proton there will be 1 neutron, and that was the primordial number that we know of. Beyond that point is what is happening between these, when the universe was 3 minutes and something like 15 minutes, these protons and neutrons, they combine and they form helium nucleus. Okay, and this helium nucleus is what is called is the primordial nucleosynthesis, and their number is something like 23%, and the rest 77% is proton. So the primordial universe that came out after 15 minutes of the creation of the universe had 77% proton and 23% neutron. These are the numbers are there, but they're still in an ionized form. I mean, protons are there, electrons are there, but protons and electrons are not combining yet. And because protons and electrons are not combining, because protons and electrons are not combining into atoms, the lights are not coming out of that soup. So we had no picture of that. We have to actually get this picture from our study in the particle physics laboratory, and from there we can understand this part of the universe. Okay, so this is what was happening, and from then onwards, the next thing that was happened is only after when the universe was 380,000 years old, and that is the time, the picture I am showing it here, when the light started coming out from the universe, when the universe was cold enough so that hydrogen and electron started combining and forming, or hydrogen nucleus, or proton and electron basically forming the hydrogen atom, and light started coming out. So this is the picture we get. So you can see now from my presentation that we can divide the evolution or the history of the universe into two parts. First part is starting from 380,000 years to the current era. This era we understand from studying the light that is coming from those objects, okay, far and far away from objects, ultimately from the 3-degree microwave radiation, background radiation. So this era is what we call the era of astronomy, normal astronomy that we know using the telescope. But if you have to go beyond that 380,000 years, that is earlier to that, from the creation of the universe, we will not understand the universe just by studying the light, because no light was coming out of the universe at that time. The universe was very dense. If we want to understand that part of the universe, that is from the beginning, not from the very beginning, because we don't know how the beginning was, we can talk about earliest time is 10 to the power minus 43 second after the creation of the universe, when the universe was something like 10 to the power minus 32 degree Kelvin. From that time onwards to 380,000 years in the history of the universe, that period we can understand from our studying, not using the telescope, but using the particle physicist microscope, that is by studying the properties of elementary particles, how they behave, and the forces, how they behave, that the forces are combining at higher and higher energy, that electromagnetic force is combining with weak force, electromagnetic and weak force, that is what you call electroweak force, and again combining with strong force at higher energy, and then at finally the strong, weak, and electromagnetic force will combining with the gravity at the at the Planck scale, and so on. So this understanding of the early part of the universe we can understand from our understanding of the particle physics. So this total picture, the complete history of the evolution of our universe, if we have to understand, you have to combine what we have studied using our telescope, but by our astrophysicists, by our astronomer and cosmologists, and what we have studied using our particle physicist microscope, that is in the accelerator, or using cosmic rays by studying the elementary particle. Combining these two, we get the whole picture of the creation or the evolution of our universe from the creation till now. Thank you very much.
Thank you very much for your wonderful presentation, sir. So it was a great webinar and so exciting. I think our students and viewers have enjoyed lots, and we have got lots of questions. So if you allow, we can start our discussion session.
Sure.
We have got question in inbox and as well as in the comment section also. So first question I'll take from the inbox. So what are the quark-gluon plasma and how it have created after the Big Bang?
So this is see, okay. The matter. The plasma. Okay, electromagnetic plasma. How do you talk about the when you are talking about the strong force? Normally, what you expect inside a nucleus, the quarks are combined together. Why they are combined together? They are combined together because of the exchanging gluons. Now, if you heat it up, as I told you, no, that think of about my concept of the melting point of different phases. Okay, ice is melting into liquid, liquid is melting into vapor. So the quark gluon plasma is when the quark has completely melted down. Okay, in the sense that now in quarks are not getting combined by the gluon, but the quarks and gluons are in a completely fluid phase.
Okay, sir. Thank you. So we have another question. So what are the Higgs boson and how we can detect them?
So Higgs boson, as I have shown you, in the Higgs boson
Yeah.
existed at temperature of 100 degree, 100 GeV. Okay, what you call the electroweak scale. Electroweak scale is where the electromagnetic force and the weak force combine, and that is at 100 degree and 100 GeV. Okay, and at that time is when, so for example, the phase transition happened when the all the particles got mass and Higgs bosons also came into existence, or Higgs bosons also got its mass.
So thank you, sir. We have
So if you
got another.
actually go beyond, if so, you see, this is
Yeah.
again a symmetry breaking, or see phase transition kind of picture if you see. So before that, there was no, sorry, okay, go to the next question. Yeah.
Okay, sir. So why did the antimatter disappear from the universe?
Disappeared from the universe?
Yeah.
This is actually a very good question, and in fact, we are still trying to find an answer why the antimatter disappeared. So actually, you are absolutely right. The way I have presented, at the creation time, matter and antimatter was created in equal
Yeah.
time, because the photons are colliding and creating matter and antimatter, quark and antiquark, electron and positron, and so on, neutrinos and antineutrinos. So all particles and their antiparticles at the beginning are in the same number. But then somewhat happened that most of the matters and antimatter annihilated each other, but a tiny amount of matter remains. And that's what we see
Yeah.
today. And why it is there? That is basically because we think the properties of matter and antimatters are little different. And this is goes by what you call a CP violation, okay, charge parity violation. And we are trying to understand that in the neutrino physics sector, that really this, if this CP violation can explain the disappearance of the antimatter. The CP violation is linked to the little different behavior of matter and antimatter. If the matter and antimatter behave exactly in the same way, then their number will remain same, and so they will annihilate each other completely. But if the matter and antimatter behave little differently, then there is a possibility of matter surviving, little of the matter surviving at the end, and that the matter and antimatter behave differently is connected to the properties called CP violation, charge parity violation. Okay, so if we can understand this charge parity, we know that charge parity violation exists in the quark sector. We have already seen charge parity violation, but the amount of charge parity violation we see in the quark sector is not good enough to explain the disappearance of the antimatter. We need charge parity violation in the electron or in the neutrino sector. If we can discover this charge parity violation in the neutrinos, that the neutrinos and antineutrinos are also behaving little differently, then possibly we'll be able to understand why the all the antimatters have disappeared, and we have only a matter-dominated universe today. So we are
Yes,
working
sir.
on
Thank
that.
you, sir. Yeah. So, sir, thank you. So now we need to go in the comment section. So the first one. So this is this the baby universe?
Sorry, what is
So
the
this
question?
is the baby. Is the so this is the
Baby
baby
universe.
universe?
Okay,
Yeah,
so what
yeah,
we are talking about the early universe. Okay, actually, if you see,
yeah.
early means
Maybe.
how early. So universe today is something like 13.7 billion years old. Okay, so our origin started 13.7 billion years ago. However, the particle physics, what I have talked about, is really all those phase transition, that one of the forces coming one apart from each other, okay, the decoupling forces, that the strong, weak, electromagnetic, etc. That happens in fast, in not even the first, 1 second. It's actually much more that very small fraction of the first second is when all these things have happened. So what I'm talking about, really speaking, is from that 10 to the power minus 43 second to something like when the universe was 15 minutes or so, when all this primordial hydrogen and helium has been formed. And beyond that is just the same. Once the hydrogen and deuteron has been formed, those hydrogen came into combine with the electron from the atom, and then hydrogen atom came, because of the gravity, they collapse and then form the first stars. And inside the first stars, all the other heavy elements was created, and then they form the next generation of stars and next generation of stars and so on.
Okay, sir. Thank you. So we have another question. So are neutrinos the first subatomic particles created after the Big Bang in the early universe, or
Well,
are they
all
the
the subatomic,
photons?
yeah, all the subatomic particles were created at the same time, but neutrinos actually decouple from the other particles. See what is happening at that time. The universe was so hot, so dense, that the particles were creating and also getting annihilated. Okay, their combined particle antiparticle is coming together and creating photon. Photons coming together, coming particle and antiparticle. So this was called the equilibrium or thermal equilibrium. Whole thing, whole soup was the thermal equilibrium. But then when the universe became little cooler, the neutrinos are the first to come out of that thermal equilibrium, because they doesn't interact that strongly. The neutrinos interact only by weak interaction. Neutrinos is the only particle which interacts only by weak interaction. And weak interaction is one of the weakest forces. So when the universe became roughly 1 second old, little cold, then the neutrinos actually decouple from the rest of the particle, and they are spread out all over the universe. In fact, today also they are there. In fact, every cubic centimeter of our space, we have something like 300 neutrinos created during the Big Bang. Every cubic centimeter. So you just imagine, you just, inside your hand, you just hold your fingers, and inside that you will be having something like 300 neutrinos in every cubic centimeter. So those are the primordial neutrinos. They came out first. The next particle that came out of that primordial soup are the photons, that's the quantum of light. And that happened. So neutrinos came out after 1 second after creation of the universe, and the light came out after 380,000 years from the creation of the universe.
Thank you, sir. Then go another question. So, is there any possibility of finding some nuclei made of top, bottom, or charm and strength quarks in some corner of the universe?
Well, actually, that existed at the early universe. In fact, if in the CERN experiment, the accelerator experiment, we do create particles that is made out of those heavy quarks. Okay, they're created all the times of the heavy quarks. But only problem is they are very unstable. So they are formed, but they would immediately decay into lower mass particles like proton and so on. So they will decay immediately. They are not stable. So they existed at the early universe, but in our universe as such. But today we can create them in the laboratory.
Okay, sir, thank you. So we have another question. So, why only our universe is made of special combination of some particles of standard model?
What do you mean by our universe? We only know about one universe. We have only one universe.
Yes. So, why only universe is made of a special combination of subparticle of standard model?
Well, this is actually very interesting. There are certain theories also why we have these forces and these particles and these things and so on. And we see we are trying to explain the nature, okay, its properties and so on. Why these particles? You are asking the question, okay? That question doesn't have any really meaning, right? Why
So,
this
thank you. So,
particle?
we
Why
have,
not some other
yeah,
particle? You are asking the question like that,
yes.
but that question has no. What we do? What is the job of a scientist? We look into the nature and try to explain the nature, try to understand
Yes.
how the nature is made out of and its properties and so on.
Okay, sir, thank you. So, what
So,
generates
for
the neutrino
example,
masses?
same reason we can't
Okay.
ask the question like why gravity exists or why there is a strong force, right?
So thank you. So what generates the neutrino masses and what are their values? Are neutrino their own antiparticles?
Very good question. I have not talked about that, but I think that my audience is very, you know, well, read and about neutrinos and their masses, and which I have not covered actually in my talk. And you are right. And this is one of the exciting areas. And till something like 30 years back or so, we used to think that neutrinos have no mass. Neutrinos are massless particles, and that's how we started. And if you are in when I was in my school or college, neutrinos had no mass. Okay, but recent experimental observation by which we have seen the neutrinos have mass, and this observation is called neutrino oscillation. And I am not going into the details, but you will see that there are something called there are. If you have seen my picture, one of these slides, I have shown you that there are three neutrinos, one associated with electron, one associated with muon, one associated with tau. So these are called three flavors of neutrinos. So we know that there are three neutrino flavor states, and we know that neutrinos, when travel, they change their flavor. That means if we start with electron neutrinos and the sun, in the sun actually a lot of electron neutrinos are created all the time. When hydrogen is getting converted into helium in the core of the sun, hydrogen is burning into helium. That's why we are getting energy. And when that is happening in the core of the sun, then lots of neutrinos are produced. And we try to detect those neutrinos. But we find that by the time that neutrinos reaches our Earth from the sun, they are not anymore electron neutrinos. They have converted into muon neutrino or tau neutrino. This oscillation of electron neutrino or conversion of electron neutrino and muon neutrino is called neutrino oscillation. And this oscillation is only possible if neutrinos have mass. In fact, from this oscillation, we have inferred, we have not measured, we have inferred that neutrinos have mass. Okay? In fact, what we have measured is the mass square difference. We don't even know, even today, what is the individual mass of the neutrinos. But we have their mass, but we also know that they have very, very tiny masses. How tiny? You know, what is the mass of an electron? And this mass of an electron is something like 0.5 MeV. But this electron mass is something like a less than an electron volt. In fact, it may be 10 to the power minus 2 electron volt, 1/100th of an electron volt, or 1,000th of an electron volt. But it may be small, but it has a mass. We know that. And we are trying to understand much more about these masses of the neutrinos and their properties. In fact, somebody was asking me that question, where is the antimatter disappeared? And I told you that
Yeah.
disappeared because of this something called CP violation. And we are trying to understand if the neutrinos have CP violation. And if neutrinos have CP violation, then this disappearance of the antimatter can be easily explained. So they are all linked actually.
sir. Thank you. So we have another question. So why the finding of exact particles, the nature of dark matter, is so difficult for particle physicists?
Well, when we started looking for dark matter, we never thought that it will be that difficult. Okay, so we had certain ideas about what the dark matter will do and what their masses are, and we started detecting them. And sir, see, for the problem about dark matter, it is not baryonic matter, and it doesn't interact by the normal interaction. Okay, but it has a mass, so it can impact. So for example, the dark matter, when going through the medium, let's say I have a medium here, some iron, so it will go through that matter or water it is going through, then it will hit the nucleus of that material, and the nucleus will get displaced little bit, or what you call, displaced little bit, or and if we can measure that displacement or impulse, that is, and that is how we started, that we will detect dark matter like that. But till now we have not been able to succeed in detecting dark matter like that way. So we have started thinking differently. Maybe dark matter properties is something different. Maybe the composition or the structure of dark matter is different. Maybe the dark matter properties are different. Okay, so maybe dark matter is not the dark matter what we are thinking of, heavy dark matter. Maybe they are very light and so on. So we are looking into different front, or attacking different front, to understand what this really dark matter is all about. We know that dark matter exists because there are many observations that support the idea that there is something called dark matter that has to exist to explain those phenomena. Okay, the rotational velocities of the galaxies in the cluster of galaxies and so on. If we study those, then we know that there is dark matter, but we have not been able to succeed.
Yeah, thank you, sir. We have another question. So, if supersymmetry will not be found in experiment, then what will be the fate of ground unification? So, ground unification, and will strong force cannot unify with electroweak force, but we know at a very early universe it existed.
So I think supersymmetry as such you don't need for the grand unified theory. Okay, grand unified theories is only combined strong and electroweak force, and you can be there without even supersymmetry. So for grand unification you don't need supersymmetry. So there is no issue. But problem is the grand unification. If grand unification occurs, that means what you are putting the proton or the quarks, and unification means what? The putting into one family. That means, see, if you remember, I have told that all these quarks and electrons belong to
Yes.
different families. Then they will come under one family, and then in that family there will be the new force, right? Grand unified force, and every force has its exchange particle. So grand unified force will have its exchange particle. Okay, so that will be different than other forces. This one. So the problem is that if there is a grand unified force, then the proton will not be remain stable. The proton has to decay. And in fact, in my career, I started my career to look for proton decay at Kolar Goldfield. I think you have told at the introduction that experiment I was doing at Kolar Goldfield is to study the stability of proton. The reason I was looking for the stability of proton is basically to see whether the grand unified theory is correct or not. Unfortunately, we have not yet seen the proton decay. But still, new experiments are coming up, and we hope in near future we'll be able to see the proton decay, and we'll be able to establish the grand unified theory is correct or not.
Okay, sir. Thank you, sir. This may be the last question. So, is there possibility to finding new particles or new force in currently ongoing muon G2 experiment in Fermilab?
Well, the the muon G minus 2 experiment is Fermilab, is actually a very interesting experiment. So you can study new particles in two different methods. One is just go to a collider, accelerator, and collide this proton antiproton very hard, go to very high energy, or using cosmic rays. and then look for new particles. Okay, so this is one way of looking at. There is another way, because these particles exist actually, even if you don't create them, they exist. And this is the beauty of the quantum mechanics, which is telling us that the virtual particle, right? The energy you can get converted into particle antiparticle, and the particle antiparticle will immediately return back and give that energy back. And this is allowed by the Heisenberg uncertainty principle. So these are called virtual particles. So in any environment, if you have a muon or if you have an electron, if you see, a electron is not a single particle. Around that electron, there are a large number of virtual electron-positron pairs going around. Quark antiquark pairs is going around. So it is actually a cluster of particles around that. So same thing what happens in a quark. Inside a proton, there are 3 quarks. But as I told you in my picture, it is not 3 quarks. There are many much more quarks, antiquarks, and gluons. They are created and destroyed. These are called virtual particles. So if there is a new particle, that particle also can be created around the electron, around the muon, okay, by this uncertainty principle, the creation of the particle and antiparticle. So once they are created, and if you study the properties of the muon, this new particle that is created inside that particle, their presence will be felt by studying the properties of the muon. And that's what this Fermilab experiment, G-2 experiment did. They were measuring the magnetic moment of the muon. And the magnetic moment of the muon will be different if there are new particles surrounding that muon. And from the measuring of the magnetic moment, whatever value they got, that cannot be explained by the known particles covering or going around the muon. You need additional new particles. So this is the indirect way of talking about or giving an idea that a new particle exists. So you can do either way. But this will only tell you ultimately that there are new particles exist. But ultimately you have to find that new particle somewhere else to really establish that new particle exists.
Okay, sir. So thank you for your wonderful presentation and exciting discussion session, sir. So it was a great webinar and exciting too, and the student and viewers have enjoyed lots as they shown their question session. So they have asked a lot of questions. So I am requesting you to, as we got a lot of questions from neutrino. So could you arrange another talk about neutrino in near future if you have time? So we can arrange. So thanks
Sure.
again,
I
sir.
mean,
And yeah,
if you are
yeah,
interested to know about neutrinos,
yeah, yeah,
because that's
yeah,
my bread and butter in the
yeah,
last 15
yeah, of
years, so
course.
I'll tell you all about
Yeah,
neutrinos.
yeah. Okay, then we can talk about it later. So thanks again, sir. And the main aim of our program is to motivate and encourage our students in this critical time, corona pandemic situation, as this is the new type of experience we are having. So we are trying to do something for our student, and thanks for helping us in doing this. So I think students have learned a lot of things about the particle physics and its role in early universe. So as we know that almost 95% of our universe is unknown still today. So we have to know. So if some of our students have feel interest in this research, so they might fall in love and do research in near future, and they might find those unknown dark matter and dark energy, sir. So thanks again, sir, for helping us and giving us this opportunity. And it's my honor and privilege, sir, to host you in our International Physics webinar, sir. Bye for today. And hopefully we'll arrange another webinar on neutrino physics in near future very soon.
Well,
Bye, sir.
thank you all. Bye.
Yeah, it's my pleasure, sir.